In this video, we will look at how to take the derivative of functions that are implicitly defined, and this is known as implicit differentiation. And this video will just be examples. So we wish to find dy dx for x squared plus y squared equals 25. All right, so implicit differentiation is going to work in much the same way. Go term by term. So we say, okay, what's the derivative of x squared? Well, that is 2x. What is the derivative of y squared? Well, that would be 2y. But y is a function of x. So chain rule says we have to multiply that by dy dx. That equals the derivative of 25, which is 0. At this point, now all we have to do is algebraically solve for dy dx. So the first thing we do is subtract 2x from both sides. Then we would divide by that 2y, and we'd be left with negative x over y. That would be dy dx. Let's now look at x cubed sine of y plus y equal to 4x plus 3. So again, we wish to differentiate term by term. This first term here is a product rule. First times derivative of the second. And don't forget, since y is a function of x, you have to use chain rule to write dy dx. Plus second times derivative of the first. And so that is the derivative for that first term. Now, derivative of y is just dy dx equals 4. We wish to isolate dy dx, so let's subtract out that 3x squared sine of y. Now on the left-hand side, we can factor out that dy dx. And finally, we can now divide to isolate dy dx. And that would be our dy dx. Now, let's go back to this example up here, and let's go ahead and find the second derivative. Right, so we want d squared y dx squared for x squared plus y squared equals 25. So what we're really looking for then is d dx of negative, I'm sorry, I don't want to write it that way. Yeah, we want d dx of dy dx, which is d dx of that negative x over y. So this is a quotient rule. That negative is a constant, so just leave it. All right, so it would be the derivative times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. However, dy dx is negative x over y, so we substitute that in. And now it's just algebraic simplification. So we have negative y minus x squared over y all over y squared. So negative y squared minus x squared all over y, and that whole thing is over y squared. I'm sorry, this should have been a plus here, which means that's a plus. So what we have is negative y squared plus x squared over y cubed. There's still one more simplification we can make. Right? Remember, x squared plus y squared is 25. So this is negative 25 over y cubed. And this would be the second derivative with respect to x. All right, next we're going to take a look at a curve that is known as the Folium of Descartes. And that curve has equation y cubed plus x cubed minus 3xy equal to 0. And we want to find dy dx at the point 3 halves, 3 halves. All right, so first we have to find dy dx. Again, it's just term by term. 3y squared dy dx plus 3x squared minus product rule. So minus 3x dy dx minus 3y. And that, excuse me, that equals 0. Keeping all of our dy dx terms on the left-hand side, we'll get 3y squared dy dx minus 3x dy dx is equal to 3y minus 3x squared. Factoring out that dy dx, three y squared minus 3x equals 3y minus 3x squared. Then finally solving for dy dx, 3y minus 3x squared all over 3y squared minus 3x. And those 3's can cancel, so we can write this as y minus x squared over y squared minus x. Now we're not done yet. We now want to evaluate this at the point 3 halves, 3 halves. So we get 3 halves minus 9 quarters over 9 quarters minus 3 halves. And with some cleverness, you should see that that is negative 1. Let's go ahead and now find the tangent line. So tangent line would be y equals negative 1 times x minus 3 halves plus 3 halves. And so we find the tangent line is y equals negative x plus 3. Now what this is saying is the slope at 3 halves of the Folium of Descartes is negative 1. Right? It's the line negative x plus 3. And finally, an application of implicit differentiation. This is known as logarithmic differentiation. So let f of x be the function x plus 1 squared times 2x squared minus 3 all over the square root of x squared plus 1. and we want to find f prime. Now, normally, this would require quotient rule, and then we'd have to do product chain, right? So this is actually a really tedious derivative to take on its own. Instead, what we can do is say this is y. Now take the natural log of both sides. So we have natural log of y is equal to the natural log of x plus 1 squared times 2x squared minus 3 all over the square root of x squared plus 1. But that can simplify using laws of logarithms to 2 natural log of x plus 1 plus the natural log of 2x squared minus 3 minus a half natural log of x squared plus 1. And now we use implicit differentiation on this. We'd have y prime over y on the left-hand side is equal to 2 over x plus 1 plus 4x over 2x squared minus 3 minus x over x squared plus 1, right? Derivative of x squared plus 1 is 2x. Those 2's will drop out. This means that y prime is y times that. Now we just have to replace y with that natural log. I'm sorry, not the natural log, with the original fraction. And then that is times 2 over x plus 1 plus 4x over 2x squared minus 3 minus x over x squared plus 1. For purposes, in this case, logarithmic differentiation was not necessary. It is necessary in certain cases, so this is an important method to keep in mind. That concludes this video on implicit differentiation. Starting with the next video, we will study applications of the derivative, beginning with a look at the marginal functions in economics.